Very good morning, friends. It's been a long time after we were doing the teachings on the whiteboard. Up to now, for almost 10 to 15, I think so, or 20 videos, we have been discussing our topics on the screen sharing apps. I think so, because of a small problem with my camera tripod, I made this. So I thank all my subscribers because of your encouragement and your support and affection. I have uploaded almost 80 videos in my YouTube channel. So thank you very much for that. So in this video, we'll just see or we'll just understand the Biot Savart's law, which forms the basis for magnetostatics. Okay, so Biot Savart's law is the basic law of magnetostatics. So that we need to understand, as we have the basic law of electrostatics as Coulomb's law. We understand that Coulomb's law as the basic law for electrostatics. Similar to that, we have Biot Savart's law as the basic law of magnetostatics. So let us understand what this Biot Savart's law gives us, or what is the statement of Biot Savart's law, how we can understand that statement. For example, I have a current carrying conductor. Let us assume this as the current carrying conductor. I considered an arbitrary shape of a current carrying conductor. So due to this current carrying conductor, as this current carrying conductor is carrying a moving charges always create a magnetic field. We understand that. So because of this current carrying conductor, I want to find the magnetic field at a particular point, right? So at this point, for example, this is the point where I want to find the magnetic field. So usually my notation is, I follow this statement or this notation. Wherever means at any point, if I want to find the magnetic field or electric field, I call that point as point of interest. So here point P can be called as point of interest. So we need to understand this. Point of interest is nothing but the point where I want to find the magnetic field, or the point where I want to find the electric field. This is called as point of interest. Now, so the thing is, I have an arbitrary shaped current carrying conductor. Due to this current carrying conductor, I have a magnetic field, and I want to find the magnetic field at this point P due to this current carrying conductor. See, you know that the current flows always through a closed path. Whenever there is a closed path, then only there will be a current. So it is nothing but here I am considering only a portion of the conductor out of the entire current carrying loop, right? And here let us assume the distance between this current carrying conductor and this point of interest. So let us assume the distance vector as r bar. So this is the distance vector from this current carrying conductor to the point of interest. Now, how can I state Biot Savart's law? See, through this current carrying conductor, let us assume a current of I amperes is flowing, and this is the small current element. Current element is nothing but a small portion out of the entire current carrying conductor, a very small portion. So this is a very small portion out of entire current carrying conductor. So let us assume that small portion length is dl. So dl is nothing but the length of this small portion length, and I is nothing but the current flowing through this entire conductor, and r bar is the distance vector from this conductor to the point of interest. Now, how can I understand Biot Savart's law? Biot Savart's law basically says two things. First thing is that The differential field means it is a differential current element, a small current element. Due to this small current element, you will have a small magnetic field. So I call that field as differential field, right? So that differential field or differential magnetic flux density, differential magnetic flux density is always proportional to the current element, is proportional to current element. What is the current element? So dl is the length of that element and current flowing through that element is I. So we can call that current element as IDL. Okay. So a differential magnetic flux density is proportional to current element and means is proportional to product of current element IDL and cosine like that. So sine of angle between so the current element, so this is the current element which is in this direction, which is in this way, and the angle between this current element and the line joining the current element to point of interest is theta. Okay, sine of angle between, let me write first in the theoretical form, then we will write the mathematical statement. Sine of angle between current element and line joining the current element and point of interest. Line joining the current element and point of interest, right? So what is that? Sine of the angle between the current element and the line joining the current element and point of interest. This is the line joining the current element and point of interest, and this is the current element. So the angle between these two is theta. So the meaning of this is sine theta. This is the first statement of Biot Savart's law, and let me write the second statement here. So, and the second statement is the differential magnetic flux density, or it may be magnetic field intensity, both are same. Magnetic flux density is inversely proportional to square of distance between current element and point of interest, distance between current element and point of interest. So this is the second statement of Biot Savart's law. Please have a look on this. Please have a glance of the two statements. First statement is related to direct relation and the second statement is related to inverse relation, right? Now from this, how can I write the mathematical relation of Biot Savart's law? Now I am writing mathematical relation of Biot Savart's law. What is that mathematical relation? dB, is it right? Differential magnetic flux density. Differential magnetic flux density is nothing but dB. So dB, let me write first in a scalar form, then we can write in vector form. First dB, differential magnetic flux density, according to first statement, is directly proportional to IDL sine theta. This is the first mathematical statement of Biot Savart's law. What is the second mathematical statement of Biot Savart's law? So it is dB inversely proportional to square of the distance from the current element to the point of interest. So r square. So dB is proportional to IDL sine theta and dB is proportional to 1 by r square. This is the mathematical statement related to first, and this is the mathematical statement related to the second theoretical statement. By combining these two, you will get dB is proportional to IDL sine theta by r square. Is it right? Now, in order to remove this proportionality, I want to introduce a proportional constant. So, dB is equal to, that proportional constant is mu naught by 4 pi, right? So, mu naught by 4 pi IDL sine theta by r square. So, the unit of magnetic flux density is Weber per meter square. We know this already. Or another unit is Tesla. So this is the mathematical statement related to Biot Savart's law. Okay. Now let me analyze this mathematical statement a bit, and we will finish off this video here, because we just this video is only on Biot Savart's law, understanding the Biot Savart's law statement and its mathematical relation, all this, right? Now if you observe, what is the direction of what is the direction of the field due to this current carrying conductor? First, what is the direction? In order to know its direction, we need to express this in vector form. Is it right or not? So how can I express this in vector form? How can I write dl sine theta? If you understand this, I am writing like this. So dl sine theta, I am writing it as dl bar cross ar bar magnitude. Is it right? Now how can I get this? Because see, if you want to know magnitude of this cross product is nothing but cross product of dl bar cross ar bar. It gives us magnitude of dl bar, magnitude of ar bar, sine of angle between, this is dl bar and this is ar bar, means unit vector in the direction of r bar. So what is that angle? Theta. So sine of angle between them is theta. Now what is the value of magnitude of ar bar? It is a unit vector, so its magnitude is 1. Hence you will get the same answer, dl sine theta. So in place of dl sine theta, what I can write? dl bar cross ar bar magnitude. If I want to write this in vector form, I can remove this magnitude. So how can I write now dB bar? So dB bar is equal to mu naught by 4 pi as it is IDL sine theta. IDL, I is a current, so it is a scalar. So I into dl sine theta can be written as dl bar cross ar bar, right? Not r bar, sorry, it is ar bar. dl bar cross ar bar by 4 pi, sorry, 4 pi is already available, so r square, Tesla. Or I can keep this in another form as dB bar is equal to mu naught by 4 pi r square I into, see this is into and this is cross product. So to differentiate between these two, I am just keeping the brackets, right? So here also I want to keep a bracket because I want to differentiate between normal product and cross product, right? So how can I write ar bar? Ar bar can be written as r bar by its magnitude. Already you have magnitude square, so you will get magnitude cube. So you will get I dl bar cross r bar, right? And here you will get another r. Let me write it directly, 4 pi r cube. So this is one form of means another way of representing. See, this is the Biot Savart's law in scalar form, which cannot give us the information about the direction of the field. Here we will get the information on the direction of field. So this is the Biot Savart's law, right? So you can express in this way, which is in scalar form, and in these two ways, which is in vector form. Okay. So this is about Biot Savart's law. So in the next short video, we'll understand some facts about Biot Savart's law. Okay. So thank you very much for listening to this video. If you like this video, please share and subscribe to my channel. And if you have any doubts, valid doubts related to this Biot Savart's law, please post them in the comment section, so that we'll try our level best to answer your question. Thank you very much.